So what's the real difference between a smooth ride and, well, total chaos? Think about it. When you're in a car, a bumpy ride is annoying, right? But when you're in an airplane, thousands of feet up in the air, it's a matter of life and death. And it all boils down to one critical, kind of invisible concept: control.
To really get a handle on control, you kind of have to understand what it's like to lose it. Some experienced pilots, they might try to show off with this maneuver called a spin. That's where the plane basically spirals down towards the ground. As the source material makes crystal clear, this is ridiculously dangerous. If you can't pull out of it, you crash. Simple as that.
And that really leads us to the big question for this whole explainer. What is this invisible force, this engineering magic that's constantly keeping these unbelievably complex machines stable and on course, even when things get a little shaky?
Okay, so let's start by looking a little closer at this whole problem of instability. It's really a constant battle, a tug of war between a system and all the forces out there trying to knock it off balance. Now, you might be thinking stability is all about having powerful engines or, the perfect wing shape. And yeah, those things are absolutely vital. But the real secret? It's something way more subtle. It's all about how a system responds when it gets pushed around. To really wrap our heads around this, we need to step out of the cockpit for just a second and into a totally different world. This brings us to what I'm going to call the saloon door principle.
No, I'm serious. Picture it. A hero in an old Western movie bursts through those swinging saloon doors. They don't just fly open and stop, do they? Nope. They swing back and forth, and eventually they settle right there in the middle. That simple motion? That's the perfect analogy for how engineers think about control systems. In fact, engineers have a name for this exact behavior. They call it time response. It's pretty much just a measure of how any system, whether it's a door or a jumbo jet, reacts to being disturbed, and crucially, how long it takes to settle back down.
Let's break that down with our saloon door. Okay, so when the door swings past the center point, that's what we call an overshoot. And if it swings back but doesn't quite make it all the way to the center, that's an undershoot. The whole game is to minimize both of those and get that door to stop in the middle as fast and as smoothly as possible.
So how in the world does a swinging door in a dusty Western connect to a multi-million-dollar aircraft? Well, believe it or not, the principle is exactly the same.
An airplane's flaps, its elevators, its rudder, all those moving parts on the wings and tail, those are its saloon doors. They are constantly moving, making tiny corrections for any disturbance, always trying to find that perfect stable center.
Let's focus on one key part. The source material brings up this great Arabic term, sukant, which refers to the rudder and the whole tail assembly. You can think of this as the main saloon door, the big one that's most responsible for keeping the plane pointed where it's supposed to go.
So when you hit a pocket of turbulence, the plane gets pushed. The control system instantly responds, adjusting the suction and other surfaces. An overshoot might feel like a little lift or dip as the plane corrects just past its intended altitude. An undershoot is that feeling when it doesn't quite get back on track right away. The system is always making these tiny corrections, swinging back and forth, to settle the plane back into that smooth flight. And this all brings us to the ultimate goal for the engineers. It's not just about responding. It's about responding in the right way. The goal, simply put, is to kill the wobble.
Because just imagine what happens if the control system is designed poorly. A tiny little bump of turbulence could cause the plane to overcorrect like crazy, then overcorrect back in the other direction, creating this violent, sickening oscillation.
The source material gives a specific and kind of terrifying example of this. In a simulation of a badly designed system, one single disturbance caused the controls to thrash back and forth 560 times before it just spiraled completely out of control. 560 wild overcorrections.
Yeah, as the lecturer points out pretty dryly, that would not be a nice flight. And that is precisely the kind of chaos that control engineers are paid to prevent.
So the engineer's goal really boils down to 4 key things. Number 1, react to any disturbance. 2, settle back down to where you're supposed to be, and fast. 3, avoid that wild back and forth oscillation. And finally, 4, achieve a stable, predictable state. That's it. That's the formula for taming chaos.
And here's the most amazing part of all of this. This principle, it isn't just for airplanes. It is the hidden blueprint for the entire world all around us. Seriously, the cruise control in your car, the thermostat in your house, the autofocus on your camera, they are all constantly doing this dance, measuring, reacting, and settling. Each one is its own little engineering marvel, constantly working behind the scenes to kill the wobble and keep our modern world running smoothly and safely.
And that leaves us with a final thought to chew on. We use all this brilliant engineering to tame the chaos in our machines and create stability. So, what are the control systems, the habits, the routines, the principles that we all use to try and tame the chaos and find stability in our own lives?